Alright guys, we're keeping it old school with my cell phone as the camera. We have a new unit, Unit 6. Trigonometry. Okay, and trigonometry is all based on similar triangles, specifically similar right triangles. And we're first going to talk about special right triangles, because there's certain right triangles that are more specialer than other right triangles. Okay, just like there are valentines that are more specialer than other valentines. Okay, all right. Page 91. Our objective is to use special right triangles and similar triangles to determine side length. Okay, so now if you already totally understand Pythagorean theorem and simplifying radicals, the next 3 minutes is going to be totally useless for you. So you can go ahead and skip ahead about 3 minutes from now or so, and it won't be a total loss for you. So we're going to do a little bit of review on Pythagorean theorem and radicals. Okay? First, Pythagorean theorem. Let me grab another color. Really running low on markers here, guys, so it won't be that colorful today. But let's look at your typical right triangle. Okay, how do I know this is a right triangle? Step 1, it has a right angle. Okay, across from the right angle, and it almost makes like a little arrow. So if we had the right angle here, it makes like a little arrow that points right to where the hypotenuse is. Okay, the hypotenuse is the longest side of a triangle, of a right triangle. Okay. The hypotenuse is also called C, and the reason why we name it C is because convention, but also typically when we label a right triangle, we start at the top with A, B, and C ends up being the right angle. So this lowercase c is across from uppercase C down here, so that happens to be the side it corresponds with. Okay, these other two sides we'll call A and B, and they're known as legs. So every right triangle has 2 legs, just like you have 2 legs. Go figure. Okay, the legs are perpendicular to each other. Always. Now the Pythagorean theorem says that a squared plus b squared equals c squared. Always. Okay, we can tell if a triangle has a right angle in it if this is true. Okay? The other thing we need to remember how to do is how to simplify radicals. Okay? So, here's the example I'm going to start with. Let's start with, I don't know, we'll start with 3 radical 250. Okay, what I want to do is I want to find the prime factorization of what's called the radicand. That's the number underneath. Radicand. So when we're prime factorizing, we're finding the prime numbers that multiply to be the product. Okay, so what I'm going to do is I want to find the prime numbers that multiply to be 250. So I'm going to start with any 2 factors of 250. So I know that 25 times 10 is 250. Now neither of these are prime. So I'm going to break it down again. 25 breaks into 5 and 5, and 10 breaks into 2 and 5. Now 5 is prime because nothing but 1 and 5 multiplies to be 5, and 2 is prime because nothing but 2 and 1 multiplies to be 2. So this is my prime factorization. So I'm going to replace 250 with 2 times 5 times 5 times 5 times 5. Find my pairs. Oh, there's only 3 5s there. Sorry. Find my pair of 5s. They get to come out as 1 because the square root of 5 times 5 is just 5. And then everything left behind gets to multiply. Okay? Just like that. All right, so let's get to the important part of today, which was the whole point, and I've already spent 7 minutes reviewing stuff. All right, special right triangle. Oh.
Hello, may I take your recyclables?
Yes, you may. All right, so we need to know how to simplify, to rationalize the denominator as well. Okay, so what does this mean? How do we rationalize denominators? Let's say I had something like 1 over radical 2. That's a problem. Okay, the reason why it's a problem, that's bad. Okay, why is that bad? We have a radical in the denominator. Okay, we need like one of those little scary face emojis. Hey, Seth. Okay, oh boy, that's scary, right?
Wait a minute,
Shh, I'm recording. I'll see you later. Come back and tell me some other time. Oh, he's scared, right? Okay, so we have a radical in the denominator. That's not good. Okay, very bad. So I want to get rid of this radical in the denominator. So I want to rationalize it. Okay, so I'm going to use the fact that x over x times 1 is still x over x. That's kind of what I'm going on here. So I know, okay, I know that if I multiply the top and bottom by radical 2, now radical 2 divided by radical 2, that's actually 1. Okay, so radical 2 divided by radical 2 is 1. Anything divided by itself is 1. So here's what's the cool thing that's going to happen, and this is why I'm choosing radical 2 over radical 2. 1 times radical 2 is radical 2. Radical 2 times radical 2, well, that's actually going to be 2. And you can check in your calculator right now. A radical times a radical, if I'm squaring this, the radical and the square cancel, and I'm just left with 2. Okay, so let's try another one. What if I had 3 over radical 5 and 6 over radical 2? So I want you to pause the video and try rationalizing this on your own. Okay, I'm hoping that you paused because I'm going to go over it now. Okay, so I'm going to multiply the top and bottom by the radical and the denominator. Okay, radical 5 times radical 5 is 5, and I just have 3 times 5 on the top. This one I'm going to choose radical 2. That's 6 radical 2 over radical 2 times radical 2 is just 2. Ooh, I have a little thing, little integers I can cancel there. So this is really 3 radical 2. Okay, and the reason why we don't want radicals in the denominator is it's just not common notation. We want to try to keep radicals out of the denominator, all right, as in any way possible. And you're going to see that this pops up later on, all right? So, special right triangles. And the goal of what we were trying to talk about today, okay? Okay. The first type of special right triangles are the 45, 45, 90 right triangles. Okay. Or the isosceles right triangles. So I'm going to draw a picture of what these might look like. Okay. Now, when we talk about special right triangles, we always base them on a hypotenuse of 1. And you'll find out later why 1 is so important, but we're going to make the hypotenuse of these 1. So when I fill these in, I've got two 45-degree angles. Okay. So I want to figure out what A and B are. Well, I know A and B should be the same since this is an isosceles right triangle, because these two angles are the same. So if I use the Pythagorean theorem to help me out, I know that A and B are the same. Okay, A equals B. So I'm going to do A squared plus A squared equals 1 squared. Well, A squared plus A squared is 2A squared equals 1. And I want to find A, so I'm going to divide both sides by 2. So A squared is 1/2. Well, now I'm going to take the square root of both sides to get rid of the square. And I have A equals, the square root of 1 is 1, square root of 2. Now this is a problem. There's a radical in the denominator. So what I'm going to do is I'm going to come over here and I'm going to rationalize it. Over radical 2 times radical 2 for radical 2 is radical 2 over 2. So A equals radical 2 over 2. Now keep in mind I just multiplied this by 1, so these two numbers are still the same. I'm just rationalized it. So in a 45, 45, 90 right triangle, the relationship between the sides is always radical 2 over 2 radical 2 over 2 to 1. Okay, and why is this important? Well, I can kind of put an x with these. Well, first off, let's back up. If I didn't want to deal with these fractions and I wanted to change this proportion, okay, I wanted to get rid of the 2 on the bottom. Well, if I doubled the length of this hypotenuse, this would stay in the same proportion. So if instead I made the hypotenuse 2, and you'll see why I'm choosing 2 here in a minute. Okay, these two triangles are similar. Why are they similar? Well, they have angle-angle similarity. So I know that if this hypotenuse is 2, if I do blue over black equals blue over black, my blue triangle was 1 over 2 for the hypotenuse. And I want to find this value here, x. The A side was radical 2 over 2 over x. Well, I'm going to cross multiply. 1 times x gives me x. And I have 2 times radical 2 over 2. These 2's will cancel because one's being multiplied and one's being divided. So x is just radical 2. So another ratio I could remember is radical 2 to radical 2 to 2. Okay, so that's another ratio. It's the same ratio as this because they're similar triangles, same proportion. Okay, and I could even expand this. I could say x times radical 2 to x times radical 2 to 2x. And what does this mean? This means that for any triangle I draw, any 45, 45, 90 triangle I draw, if this length becomes 4, okay, well, that's my 2x. So to find x, I divide both sides by 2. I get 2 equals x. So this side must be 2x radical 2, or 2 radical 2, because I found x is 2, because 4 was equal to 2x, and did it that way. Okay? So this is one way to remember the proportion of the sides. Okay? And a 45, 45, 90 right triangle. So that's the first type of special right triangle, and you need to memorize this. Okay, so pick one of these 3 to memorize that they go with 45, 45, 90 right triangles. And these are referring to the side across from the 45 angle, across from the 45 angle, across from the 90-degree angle. So 1, radical 2 over 2, radical 2 over 2. The next type, type 2, is a 30, 60, 90 right triangle. Okay? And the reason why this one is special is it comes for the other type of special triangle. We have isosceles and we have equilateral. So if I were thinking of an equilateral triangle, okay, I'm doing my best to make equilateral triangle here, of all 60 degrees and a side length of 1, because remember the side lengths of 1 are important, I can make a right triangle out of this. And I do it by dropping an altitude and making a right angle. So if I pull this right triangle out, okay, and I look at it, this bottom angle will be 60, this angle right here will be 90, and this angle up here is half that 60-degree angle, so it's going to be 30. So this is why this is the other special type of right triangle, because it comes from an equilateral triangle. Now we can't have an equilateral right triangle because the hypotenuse has to be longer than the legs, but this is how we would get our 30, 60, 90 special right triangle. So now I want to find A and B. So B is a little bit easier to find this time around. Since I know that this is an equilateral triangle up here, 1, and this whole length is 1, okay, I know that the altitude of an equilateral right triangle cuts this in half. So this being 1, this section over here to the right of the altitude is going to be 1/2. So B would be 1/2. Okay, so the altitude cuts this in half. This is half of it. So I really only need to find A. So again, I'm going to use the Pythagorean theorem. Okay, and I'm going to start with A, I don't know, B is 1/2, C is 1. And I'm going to do some algebra here. I've got A squared, 1/2 squared is 1, 2 squared is 4, 1/4, 1. All right, I got to get A by itself, so I'm going to subtract 1/4 from both sides. I get A squared equals 3/4. So now I need to take the square root of this. I have A equals the square root of 3 over, and the square root of 4 is just 2. So that's much easier. No need to rationalize anything here. So A is radical 3/2. And this proportion holds true for this as well. So 30, 60, 90. The angle across from 30 is 1/2, or the side across from angle 30 is 1/2. The side across from angle 60 is radical 3/2. The side across from 90 is 1. And notice, as the angles get bigger, so do the sides across from them. Okay. Now again, fractions are not always our friends. So let's look at this in terms of a side length of 2. So if I make an equilateral triangle, and this time it's going to have a side length of 2, I'm still going to drop that altitude, 60, 60, and this would be 30 and 30. Okay. This whole length I know is 2, but half of it, this part over here, is going to be 1. And I still want to find this value over here. So I'm going to do A squared plus B squared equals C squared. The hypotenuse is 2. B is 1. I'm still trying to find A. So 1 squared is 1. 2 squared is 4. Subtract 1, subtract 1. A squared is 3. So I take the square root. Oh, this is very nice. A squared is just radical 3, and I can't simplify that any further. So A was the side across from 60, and B was the side across from 30. So B is 1, A was radical 3, and 90 was 2. Okay, and then I can put x in with this as well. I can say 1x to x radical 3 to 2x. Okay, so I could scale this up as big as I wanted to go. Let's say I wanted to get kind of crazy. Okay, and do 5. All right, so if this was an equilateral triangle, when I had the other 5 over here, this length down here would be 2.5. This would be 30. This would be the 60. Okay, and if I wanted to find this length over here, it would work out again so that this would be whatever x is, or whatever x radical 3 is. So x in this case is 2.5, right? Because this should be x. Okay, so this would be 2.5 radical 3. And if you don't believe me, you can do the math on that and see that it works. Do the actual Pythagorean theorem, a squared plus 2.5 squared equals 5 squared. And see that it does, in fact, work. All right, I'm verging on 25 minutes here. These are good long notes. Hopefully you watch all of them. If you watch all of them and you tell me your name when you walk into class on Tuesday, I'll know that you watched them. Talk to you later.